Okay, so let's determine the direction of current. To determine the direction of current, you use your right hand rule. We use what we call a right hand rule. Now, basically, a right hand rule, you take your thumb. Your thumb must point in the direction of the North Pole, and then you curl your fingers around the wire, around the coil or a solenoid, around the solenoid. You curl your fingers. So your fingers will point, your curled fingers will point in the direction of the current. It will indicate in the direction of current. So you just ensure that your thumb points in the direction of the north in this solenoid. Then you curl your fingers. Your curled fingers will indicate the direction of current. And then you do this in the front wire. So when you look at this solenoid, the front wire is this one. This is the front wire because we can see it's continuous. But this one here that we see here is the back wire at A. That piece there is the back wire, right? A back wire is not continuous, right? It has got, yeah. So now what you do, you take your right hand, it points in the direction of the north. In this case, this is our north, so it points in the direction of the north. And then you curl your fingers. So when you curl your fingers, you'll realize that in front, so you go to the front wire. This is happening in the front wire. It is the in front, your fingers in front, they are going up like this. You are going up, and then at the back, your fingers are pointing down, right? At the back, your fingers are pointing down. Then in front there, they are pointing up. So now the direction of current, therefore the direction of current is in this case is from B, because we are moving like this, going up, and then at the back we are going down, right? So it is the direction of current is from B up to A. Then when we look at diagram number 2, to determine the direction of current there, I identify the front wire. Here is the front wire. This is the diagram, the diagram for diagram 1. The diagram 2. This is diagram 2. The front wire is this one here. This is the front wire, which is this one here. Okay? And then this is the back wire. Now what you do, you take your right hand. It must be closer to the front wire. Your right hand must be closer to the front wire. Now with your thumb, you point in the direction of the north. So the north is this side with your thumb. Then you curl your fingers. You curl your fingers. You curl your fingers. So as I'm curling the fingers, I can see that in front I'm going up. As I curl my fingers, in front I'm going up, whereas at the back we are going down. So the current here is from A up to B, because in front we are going up, then at the back we're going down, as indicated here as I'm indicating it. I said You point in the direction of the north, then you curl your fingers like this. Curl your fingers, you curl your fingers. So you can see that in front, what you see in front here, you see you are going up, but at the back, your fingers are pointing down, meaning the backward must point down, whereas the front must point up. And then in that way, we are able to see that the current is going from A up to B. Then we look at this one. We want the direction of current in diagram 1, whether it is from A up, is from X up to Y. Okay, so you identify the front wire. This is the front wire. Right, now you take your right hand. With your right hand, you must point to the left. The thumb must point to the left. This is the front wire. Your thumb must point to the left. When it points to the left, then you curl your fingers. You curl your fingers. You curl your fingers. Meaning, you will see the side of the palm now. All right. So I have pointed in the direction of the north with my what? With my right hand. And then I curl my fingers. So now, just like this, or diagram number 3. So I'm looking at diagram number 3, just like this. So this is your front wire, okay? Like I've indicated here, like I've indicated there. Right. Now, in this front wire, so I always point, your thumb must point in the direction of the north, and then you can see your curled fingers. You see in front, your curled fingers in front is pointing down in front, okay? Whereas at the back, it is pointing up. Automatically, it's pointing up, because when you curl your fingers, so when I'm looking at this thing in front here, in front, this is curling down, okay? The fingers are curling down, meaning at the back there, it's going up, right? So the front is going down, so I indicate it on the front. So then automatically, at the back, then it becomes up. So it means now the current is moving from X to Y, because I move from like this, like this, like this, like this, until I get there, right? So now for the second one, for the diagram number 2, if you look at diagram number 2, okay, you identify the front wire. The front wire is here. There is the front wire, okay? Now you point with your thumb. We point in the direction of the what? Of the north. Then you curl your fingers. You curl your fingers. You curl your fingers with your right hand. You curl your fingers. Right. So now, just like this, let's look at it. So this is the front wire, okay? You indicate the front wire. Now, what is happening in front? When you identify the front wire, you check what is happening in front, and then what is happening in front will be the opposite of what is happening at the back. So you point in the north direction with your thumb. Then your fingers, your curled fingers are pointing down. Do you see that? In front, looking at the front, the curled fingers in front are pointing down. So I indicate in front the curled fingers are pointing down. Automatically at the back they are pointing up. But what is the direction of the current? So if I'm saying up and I'm saying down like this, so it means it moves from where? From here like this until we go to X. So the direction is from Y up to what? Up to X. In this case. So this is how we determine the direction of current using right. We continue. Now we want to determine the polarity. Okay, we want to determine the polarity. So now this is a bar magnet. This is a bar magnet. Now this bar magnet has got a north pole and a south pole. Your focus should focus on the front pole. The front pole. You focus on the front pole. Now, this is what is happening. When you take a magnet and you want to push it into the solenoid, okay? When you try to push it into the solenoid, this is what will happen. The solenoid will want the bar magnet to go out. When you push it in, the solenoid pushes it out. It wants it out. Then, but when you pull the magnet out, when you pull out the magnet, the solenoid wants it back. So it says come back. So in, it wants it out. Then out, it wants it in. So that's what happens. It does the opposite. So here, it is because when you push in the magnet, you are inducing the current. Now the current that is induced is going to oppose the magnetic flux that is creating it. Remember, when you push in the magnet, there will be a change in magnetic flux, and this change in magnetic flux will induce current, and that current that is induced opposes the change in magnetic flux that has induced it. Okay, so in now we are saying, okay, we are putting in the north pole in here. So remember, if I want to put in the north pole, the solenoid will want the magnet to go out. Will you push it in? The magnet wants it to go out. It wants it to go out. Right. So it will create a pole. It will do that by creating a pole that will repel this, because when you push it in, it wants to repel it. So here Z must be a pole that repels the north pole. And the pole that repels the north pole is what? Is the north pole as well. Okay? Now, when you pull the magnet away, when you pull it out, you are pulling out the north pole, right? If you pull out the north pole, now remember the solenoid will want it back. It wants now the bar magnet to come back, right? So now it must create a pole that will bring the north pole back, because you are pulling out the north pole. I said you focus on the front pole, this one that is closer to the surface of the solenoid. The one that is closer to the surface of the solenoid is the pole that you focus on. So now check. when you pull out the magnet like this away, the solenoid wants the magnet to come back. It doesn't want it to go away from it. So it will create a pole that will bring back the north. And the pole that can bring back the north is what? Is the south, because it will attract it. Right? So 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 that is south, and automatically this side will become north. This side I said is north, automatically it becomes the what? The other side becomes the south. In this case, the same thing. You push in the magnet. When you push in the magnet, right, with a south pole, you focus on the front one. You push in with the south. So you are putting in the south. When you put in the south, it doesn't want the south to come in. It wants to repel it. So it will create a pole that will be the same as it. So that will be the south pole, so that it's repelling it. When it is coming it wants it to go out. So it creates a pole that will repel it. So it becomes a south pole. X becomes the south pole. And then at the back is north pole. Now when you pull it out, right? When you pull it out, you are pulling out the south, right? When you're pulling out the south, the solenoid does not want the magnet now to be going out. It wants to bring it back. So it creates a pole that will attract it back. So it is what? It creates a north pole, because a north pole will attract this south pole, so that the magnet comes back. And it automatically at the back becomes the what? The south pole, right? So so when you push in, these poles become the same. But when you pull out, it becomes opposite pole. The pole becomes opposite, as we can see. So out, opposite, in, same.